Okay, good day, everyone. Today we want to look at the processing of integrated circuits. Okay, right. Just a recap from our previous lectures. Okay, in our last lecture we looked at semiconductors, and we discovered that semiconductors are divided basically into two types of semiconductors. We have intrinsic and extrinsic types of semiconductors. Then we also saw that semiconductors are mainly used in the production. We want to understand what is an IC or an integrated circuit, and also what are the components. Then we also want to understand the different types of thin film depositions that are found on integrated circuits. Okay, right. We have all at some point in time uh, came across such kind of a component when you open either a computer or you open your phone or any electronic gadget. You have made some type of this kind of component or some kind of a chip like this, especially on your printed circuit boards, what are called your printed circuit boards or your PCBs. Okay, right. So what is that? On your PCBs, these components that you find are often referred to as microchips. Okay, we often refer to them as microchips. What are microchips? These are integrated circuits, okay, which comprise a large number of electronic components that have been fabricated on the surface of a substrate material, usually silica, that is in the form of what are called thin wafers. Okay, so there are other several definitions of what an IC circuit is that you can find as you do your literature review. Okay, it can actually be called an assembly of electronic components that are fabricated as a single unit. Okay, um, the single unit in which the miniaturized active devices, which are your transistors and the diodes, as well as your passive devices, which are your capacitors and resistors, and their interconnections are built up on a thin substrate of a semiconductor material, which is, as I said before, typically silicon. Okay, right. So, what actually happens in a microchip? Okay, in a microchip, there are what are called MOSFETs. Okay, and what are MOSFETs? You will find this word in most of your texts when you're actually uh, studying about your microchips. So MOSFET is as an abbreviation which stands for metal oxide semiconductor field effect transistor. Okay, so in your IC, you will find that these MOSFETs or these transistors are actually one of the largest number of things that are actually integrated into a microchip. Okay, so of importance, the components that are usually found on ICs are usually transistors and capacitors. Okay, so the purpose of a capacitor is basically to store data in a digital format. Okay, those are the purposes of capacitors, and then transistors will act as your electrical switches. Okay, right. You find that in the mid 20th century, 1950s, 60s, your IC circuit was comprised of a few electrical components. Whereas now in the modern 4IR, you can see that your ICs can actually carry several billion components. Okay, in a space which can be equal to that of a small postage stamp. So the IC components, the increase in technology or the development of technology is now making these IC components reach even to atomic scale. Okay, right. So without these achievements, most of the technology that we are using now, most of the technology that we're using now in your, especially in the internet, in your artificial intelligence, in your communication devices, etc., most of that technology would be non-existent. Why? Because it would be having robust or very big components for it to be carrying out the functions that it is carrying now. But now, because of this effect that a component can IC can carry several billion transistors, it is now possible to for us to have all these kind of systems in our in our in our in our world right now. Okay. As an interesting fact, it is said that humans now produce more transistors per year than the grains of rice. This shows how immense technology is being used and being consumed by us, the technology. Okay, right. So fabrication of your ICs involves several hundred individual processing steps that actually may require weeks to a month time to produce in order for an IC to carry out a certain type of function that it is supposed to do. So I find that these several hundred individual processing steps might be a replication of the same types of processing steps, but however, you'll be varying some of the stages so that um, you create an integrated circuit that is able to fulfill the functions that you'd want. Okay, so what are these some of these processes that we'll see as we go into the lecture? We will see what are called the deposition of thin layers. Okay, we also see what addition of dopants. Okay, yes. So these are some of the things that we'll look at. You need to keep in mind that the cost of producing these ICs is one of the most and expensive processes to be made. And to build a modern IC facility, you require actually a lot of capex for you to be able to go into that business. A lot of capex and also even a lot of opex. Okay, to maintain that business. So this is an example of a silicon wafer, and you're producing your integrated circuit. Okay, all right. So what are these silicon wafers that we are talking about? So before you start making a microchip or an integrated circuit, you first have to design exactly what you want, and this is done using very advanced computers. Okay, so designing an IC can be compared to designing a small city from background. You're starting from background and you're now building those big buildings, and designing where exactly to put each type of a building. Okay, so your starting material when we do any design of an AC, you need silicon. Okay, so this silicon is crafted into what are called wafers, okay, which are of 99.99% purity silicon. Okay, so when you have created these wafers, you then now input your components such as transistors into the layers of the silicon. Okay, so a single wafer in the production of these microchips can actually contain thousands of individual ICs. Okay, right. So the wafers are made or grown using a technique which is called the Czochralski growth technique. in which a small pure seed of crystal is used to grow a very large single crystal of silicon. Okay, so the the seed crystal is slowly rotated um, and inserted into the molten silicon bath, and then it is pulled slowly out of the molten silicon bath. So the silicon atoms then attach on the seed crystal in a desired orientation as the seed crystal is retracted or removed. Okay, so usually you require single type of crystals, okay, for your wafers. Why? Because you need uniformity in your in your substrate material. Okay, so let's look. This is the growth technique for growing single crystals in your silicon. Okay, so here you have your seed crystal. Okay, and here you've got your reactor. Okay, this is your reactor in here. Okay, which is a crucible. Okay, crucible type. So which means this is a heat refractory material. Okay, and then here you've got a bath or bath of molten silicon. So you first insert this seed crystal in this molten bath of silicon, and then you rotate it, okay, at a certain speed. And then when you rotate it, this molten silicon grows on this seed crystal. And then when it grows on this crystal, you then remove the what is called a silicon ingot. Okay, then you can now machine it into different types different shapes depending on the IC fabrication machine. Okay, then from then on, you now go on to produce your ICs. And when you've produced several ICs, you cut into just one chip because here there can be millions of chips here on your wafer. Okay, so you make with many thousands or hundreds of thousands of these microchips, and then you can now separate each chip to perform the functions that you want it to do. Okay, right. So let's look at the overall steps in the processing of semiconductors. We want to produce an FET semiconductor device. So what's the first stage? We have got our P-type silicon substrate that we have made using the procedures in the previous slides. The first stage, we allow the surface of this pure silicon substrate to be oxidized. Okay, so that's the first stage, which is oxidation. Okay, we allow the surface of the silicon substrate to be oxidized. That's the first stage, which is oxidation. After oxidation, there comes a process which is called photolithography. So for your photolithography, you take what is called a photoresist. Okay, you take you make what is known as a photoresist here. Okay, so a photoresist is a photosensitive material that is actually deposited on top of the oxidized surface of the silicon substrate. Okay, then what do you now take what is called a photomask. Okay, a photomask, and then after putting the photomask on top, this photomask is actually like a stencil. It is cut and it has got openings of the types of for the following procedures that you would want to put. So it might have some very square openings with very small square openings that will be utilized in the following stages. So on this photomask, you then allow some ultraviolet radiation to pass through. Okay, and then on the openings, where there are openings, okay, where there are openings, the the ultraviolet will actually pass through, and then where there are no openings, the photomask will actually hold the like for example here will actually hold the ultraviolet radiation. Okay, so that's the second. The third stage is actually called dissolution. Okay, So dissolution um, results now in the for example, in these portions, this portion here, okay, um, the photomask the did not allow ultraviolet to flow through. So here you can see that our photoresist material is there. But on this end here, the photomask allowed the radiation to pass through. So you can see now there is an opening here because radiation passed through. At this point here, there was no radiation that passed through. So we still have got our photoresist material. And then at this position here, you can see that the photomask allowed the radiation to pass through. So we can see that here that there is um, our photoresist material has been removed. So we now dissolve the the dissolution of this photoresist material here. It is actually dissolved. So that's the dissolution. When your ultraviolet passes through this photoresist, then it causes dissolution to occur on this substrate wafer. Okay. Then the fifth stage is actually um, called etching. Okay, what does etching do? Okay, etching now removes the exposed silica. Okay, first of all, we have removed the photoresist using the process of dissolution. Now, etching further removes now this silicon that was exposed. So this is the process of etching. Etching now removes these silicon dioxide that was exposed or to which where the ultraviolet light had passed through. So it is actually etched. Okay. Then the fifth stage is actually called doping. Okay, so we started with the P type of a silicon substrate, and now we introduce doping by an N type of a dopant. Okay, that is what we introduce here on the uh, edged or exposed silicon surface. Okay, so we introduce here an N type of a dopant where there is a source and where there is a drain. Okay. And then the sixth stage now, after introducing here your N type of a dopant, you now allow oxidation again to occur on the surface here. Okay, there's oxidation again to occur, sort of like to cover what's happening inside this wafer. Okay, so your oxidation, then you have got your SiO2 layer. Okay, then the last stage now is what is called lithography. Okay, so your lithography, you again continue like simple like what we had done here, and then you prepare or make a photoresist material on the surface of the substrate. Okay, so this is how you make a microchip, okay, or an IC, okay. All right. So now, because you want of um, several types of ICs that have got different types of applications. So the way that you position these and the way that you introduce your dopants, you need to repeat these stages in order for this IC to perform the functions that you want it to perform. So um, actually you when you do photolithography, you actually now introduce other components and even the electrical connections for the devices. Okay, Okay, so um, following the production of silicon wafers, there are actually four major classes of IC fabrication procedures. Okay, so you've got your back end processing, your front end processing, sorry, back end processing, quality analysis, and then your packaging. So let's look at the front end processing. So front end processing comprises steps of which your electrical components are created in the outermost surface region of the semiconductor wafer. So it is important to note that most of the thickness of the wafer exists merely as a mechanical support. Why? Because the electrical active components are formed on the surface and only typically extend a micron scale actually into the wafer. So this processing may include hundreds of steps. So in our previous slides, the one that we showed, the schematic diagram that we showed of producing your FETs is actually a front-end processing step to produce what is known as a field effect transistor, FE transistors. Okay, okay. So now let's look at back-end processing. Okay, so back-end processing entails the formation of a network of interconnections on or just above the surface of the wafer. So in this case, the interconnections are formed in the thin films of the material deposited on top of the wafer and are patterned into precise networks. Okay, then it forms basically serve as a three-dimensional conductive pathway um, so that the IC is able to perform or some mathematical and logical operations or even store and retrieve data. Okay, so your back-end processing ends with protective layers of material that prevent mechanical and environmental damage. We're going to talk of the thin layers in the next coming slides. Okay, all right. Okay, so after your back-end processing, you then subject your wafer to some testing procedures, both the individual wafer and then the individual chip, sorry, and then the whole wafer as a whole. Okay, so you find that there are some fractions of the chips that will be actually be malfunctioning. Okay, okay, so these can be discarded. Okay, right. And then those that are accepted, that pass the quality analysis, will then go for the next stage. Okay, then you do your packaging. So this is the last step in your producing your functional ICs, during in which the wafers are now cut apart now to produce individual physically distinct microchips. Okay, all right. So right. So packaging basically is to protect the microchips from your damage during the the transportation stage. Okay. So you can see that I'm sure you know that a computer powered by a single microprocessor actually contains many other chips for several other functions. So you can have an IC1, IC2, IC, IC3, which are all integrated circuits or chips, but performing different distinct types of functions. Okay, for example, in your computer, yes, many single microprocessor, but many chips that perform different types of functions. Okay, okay. So integrated circuit fabrication depends on part on the deposition of these thin films of materials onto a substrate. Okay, then this is the process of creating and depositing thin films onto a substrate coating. Okay, And then these films are actually made of different types of oxides or compounds. Okay, so the coatings has got different purposes and different characteristics. Okay, some may be required to alter or improve some element of the substrate performance. Well, some may be actually durable and scratch resistant. Others meant to actually alter the conductivity of the electricity or even transition of the signals, depending on the purpose of the microchip. Okay. However, it's important that you to know that the thickness of this thin film is actually at very small at a micron scale. Okay, right. There are quite a number of ways that you can actually use to do your deposition of thin films onto your ICs. However, the general technique is that there has to be a source material for a source for the material that you intend to deposit. Okay. Then there has to be a means to transport the material from the source, okay, to the workpiece, okay, to the workpiece surface upon which they is supposed to be your thin film is supposed to be deposited. Okay. Then most of these techniques actually require you to have a vacuum system, while others may be required to have a liquid environment. Okay, so we found that these deposition of thin films are actually important in many devices, as shown by here your medical implants, your LED displays, etc. Okay, so one the first method of your thin film depositing is actually called your physical vapor deposition. Okay, so in here there is a vacuum chamber which creates a low pressure vapor to the material to be deposited. So some of this vapor condenses now on the workpiece and then formation of your thin film. Okay, right. So for your PVD, you find that the coatings are actually highly durable, resistant to scratching and corrosion, and quite tolerant to high temperatures. So if your IC is going to be working in components or equipment that operates in high temperatures, then you need your PVD to be your method of deposition of your thin films. Okay. Then also your solar cells, eyeglass, and other semiconductors also makes use of PVD. Well, the disadvantages of this PVD is generally its cost is very expensive as it requires large investment when you compare it to other deposition processes. Okay, well, basically, PVD methods themselves also vary because they're different types. You have got your evaporation, then you've got your ion beam sputtering, and then you also have got your magnetron sputtering, which is the most expensive. Okay, all right. So what is evaporation? This is a simple depiction of evaporation on the right side. Okay, so evaporation, here you've got your electron beam evaporation. Okay, so in this process, um, a highly charged electron beam um, evaporates um, evaporates the target material. Okay, so you've got your electron beam here. Okay, this is your electron beam. Okay, um, and then here is your molten sample here. Okay, then this sample here is actually um, when acted upon by this electron beam, it actually evaporates, and when it evaporates, it then forms this thin film, this coating on this IC that you want to be coated. So this is process which is used for your optical thin films, etc. Okay. Then you have ion assisted deposition, also is part of your evaporation. In here you have your ion gun, okay, your source of your ions, okay. So it produces high energy beams, okay, that are directed to the sample, okay, or the substrate material. So these ions now impart energy on the deposited metal, okay. The deposited metal here, they impart some energy, then they resulting in a higher film density than the one that is achieved using evaporative, purely evaporative method. So when this energy is imparted on the when this energy this imparted energy on the deposited metal, it acts like atomic sized hammers. So because of the action of these atomic sized hammers, it is the one that actually now results in this high film density on the substrate material. Okay. So because of this high film density, you can rest assured that you've got more mechanical durability and more environmental stability that occurs when you do ion assisted deposition. Okay, then you've got your thermal evaporation, which is very simple. So for your thermal evaporation, you've got a heating source, and then you've got here your target material here, which is to be heated. And then when this material is heated, it then evaporates. And after evaporates, it then forms a thin film on this substrate material here. So there's a thin film that forms here on the substrate material here, which is brownish in color. So this is used in your solar cells and also your thin film transistor. Okay. Then you've got sputtering. Okay. So this is actually the most important PVD method for your IC manufacturing. Why? Because the interconnections that carry electrical signals from one electronic device to another on an IC chip are typically made of aluminum alloys that have been deposited using sputtering. So in the sputtering, first of all, argon or other types of gas ions are first ionized and then accelerated by an electric field towards the source, okay, to be deposited, okay, which is your target. Then these ions dislodge and eject atoms from the surface of the source material, okay, some of which drifts across an energy gap towards your workpiece, okay. Right, so those ions that condense on the surface are said now to be deposited. Okay, so that's your sputtering method. Okay, so here is an example of sputtering using a magnetron. Okay, so a magnetron is a plasma-based coating technique. So in this process, um, your plasma, which is magnetically confined, is created near the surface of the target material. Okay, okay. So ions. Here you've got your this is your magnetron, your cathode uh, magnetron. Okay, so ions from the plasma. This is now your plasma here. This is your plasma. Collide with the target material. Okay, and the atoms that are ejected here. Okay, atoms that are ejected here from the collisions are are, are the ones that are sputtered, okay, all directions. And those that are sputtered in all directions, however, some will be directed to the substrate material here, and that is where deposition occurs. Okay, so that's magneton sputtering. Then you also have got your ion beam sputtering. Okay, so you've got your source of ion here. Okay, all right, so you've got your ion source here. Okay, so this process uses an ion source to sputter the target material. Okay, which is usually a metallic or a dielectric substrate. Okay, so the thin films created through the ion beam sputtering are actually now, in this case, of high quality, and they're very precise thickness due to the monoenergetic ion beam that is actually used here. Okay, right. So this process is used to create precision of optics for your semiconductors. So where precision is actually required, you have to select the ion beam sputtering. Okay. Then you've got your pulsed laser deposition. Okay, so in this pulsed laser deposition, you've got your high power, um, your source of the source here of your pulsed laser beam, which is focused on the surface of the target here. Okay, which is focused on the surface of the target here. Okay, then energy is then converted into electronic excitation and then thermal, chemical, and mechanical energy. So there is rapid evaporation of the target, which produces a luminous plasma plume. So this plume now is the one that contains atoms, molecules, or ions. Okay, and when it rapidly expands into the surrounding vacuum, it condenses now as a thin film layer on the substrate as shown here. So that's your pulsed laser deposition. Then you've got your chemical vapor deposition. Okay, in this case now you've got your source of gas. In this example, you've got your argon. Okay, so it is introduced into a heated chamber. This is your heated chamber where it undergoes some chemical reaction. You can see the temperature is increasing 200, 500 to 800 here. So during this chemical reaction, it produces a desired material as a product. So this this product that is produced is then allowed to condense on the surface of the workpiece. Okay, so that's your chemical vapor deposition. Then you've got your electrodeposition, okay, which is a very simple and old technology. Your workpiece and the source is actually allowed to be immersed in a liquid electrolyte and connected by an electrical circuit, okay, which is very simple. This one, okay, and you apply a certain voltage, okay, between the source and the workpiece, okay. So ions of the source material, if your source begin to dissolve and then um, they drift towards the workpiece, okay, and chemically bond on the surface. So that's your electrode deposition, which is very simple. Okay, so here is a quiz that I would like you to attempt, um, okay, which is due in a week's time. Okay, I hope you have all understood the process of your integrated circuits. Okay, this is the end of our lecture. Thank you.